towards the end, we are going to focus on some application, let's say, not just hydrodynamics of two-phase flows in small channels, but also mass transfer. And I think Professor Ghosh will also be talking about reactions. So what I'm going to mainly focus on is separations, and in particular, solvent extractions. Yeah, come in. So we kind of go a little bit more difficult as we proceed. We'll have the separations, which doesn't involve reactions, it's physical processes, and then we'll do the reactions as well. So again, just to wake up everybody and to remind things, why do we want to, why do we want to use small channels to do mass transfer operations like extractions? And let me see. Oh, yeah, it does play. Okay, so extractions, for those of you that are not chemical engineers, are separation processes that involve two liquids. It is when it's a separation process when we try to get a material from one phase, usually an aqueous phase, to another phase, usually an organic phase, that has also particular extractants, chemicals that help this separation. And again, for those with some chemical engineering backgrounds, traditionally separations, extractions are happening to mixer-settler things, systems, which are involved in stirred vessels. And here is a stirred vessel and a two-phase flow in a stirred vessel. So we see that there is a lot of homogeneities. There is a wide size distribution of the dispersed phase. So all these stirred vessels are not very well characterized, and which means that their scale up, they're difficult to predict, and their scale up is difficult. And of course, measurements are not accurate as well. And this is because depending on where do you put your measuring equipment, your probes, you might pick up different parts of this process. And a lot of these extractions, and this is another thing I will mention as a different way of intensify a process, is that a lot of these extractions involve organic solvents. Organic solvents can be hazardous. They have low flushing points. They might have other health hazard ratings. But also, a lot of them are oil derived. And again, there is this tendency to move away. So the proposition, the suggestion is that we move from this type of equipment or processes to this type of processes in small channels, and we operate, which operate continuously as well. Again, for those with some chemical engineering background, we are going from something that is in a batch scale to something that is in a batch approach to something that is continuous. So we will be using our small channels and with all the properties we were been discussing the previous days to do now our extractions. And just repeating the same thing, we get in these small channels, we get what we want, which is process intensification, which means that we have enhanced heat and mass transfer rates. The very large transfer rates means that we reduce the concentration gradients, we have more uniform conditions, and this means that we can actually do accurate measurements. And also the modeling is more easy, especially because, as you will be seeing in the next two tutorials, flows are mainly non-turbulent, so the modeling can be more easy and more accurate as well. And of course, we have this increased surface area to volume ratio, some of these things we discussed before, which means, and this is an advantage, that, okay, we have the nice flow patterns like a Taylor flow, but also there is this possibility of manipulating the flow patterns. And we discussed a bit in the previous days that, yeah, depending on how we introduce our fluids, the wetting properties, we can change the flow patterns. So there is this possibility here. What I will be looking at, and this is some two systems that people have been doing a lot of work, is how we can intensify separations working in small channels in Taylor flow. In this is Taylor plug flow, segmented flow, but also a kind of different type of or unit we are using, which is this impinging jets. And I will discuss that a bit more in the context of scale up as well. The other thing that, again, people have started doing a lot of work and offers a lot of possibilities for actually collaborating also with chemists, is that because of all these intensified processes, because of all this intensification, one advantage we have is that our inventories, the fluids, the amount of fluids we use can be less and better used, which means we can now start thinking about not the standard solvents only that have been traditionally used, but also of solvents, novel, let's say new types of solvents that have a number of different benefits, and some of them could even be considered green. Okay, they don't have all the let's say the problems that the organic solvents have. And the two types of solvents we have looked at is these ionic liquids, and there is a lot of work on this, but also aqueous biphasic systems. And I think somebody here have said they have already used those as well. A couple of things about these two different types of solvents. Have people heard ionic liquids before? Have you used them? Yeah. So basically, what ionic liquids are salts that are a liquid in room temperature. And they have some very good properties, such as negligible volatility and flammability. And there is a lot of discussion and a lot of work to try to make them what we call task specific. So the people try to modify them. So in a way, they enhance a separation. So they act as extractants as well, rather than just a diluent, just a solvents. They have some disadvantages. They are expensive, at least so far, and they tend to be viscous compared to traditional organic solvents. So by using small channels, we could perhaps alleviate or go some way into meeting these problems, these challenges. The first thing is that because we intensify the process, we can reduce the amount of solvent we're using. So the cost might not be as significant. And because we can play with the flow patterns, there is a possibility to reduce this effect of viscosity. So if we have a flow pattern where the ionic liquid is not in contact with the wall, then perhaps we can reduce the pressure drop. And we don't have this problem with a high pressure drop. It's what people used to do in the past with using water in water oil flows, using water to transport heavy crude oil. They were working with annular flows. Yeah, exactly. So actually the viscous phase was not in contact with the wall. So this is the advantages that we can explore and exploit in small channels to actually make possible the use of these ionic liquids as well. Another system is these aqueous biphasic systems. And in case you have not come across it, the system is what it actually, the name says. Traditionally, or the more common ones, are the systems that are made with water, and people put some polymer and some salt inside. And after a certain concentration, the one phase separates into two. Okay. And the good thing is that although we have some salt and some polymer, the majority is water. Okay. What we have done, because we have been working with ionic liquids, is instead of using polymers, we used ionic liquids and salts to create these aqueous biphasic systems. So we actually have water, we put ionic liquid with salt, and then after certain concentrations, we have two phases. And we have done some work on that one. These systems are not new in a sense. Involving the ionic liquids is more recent, but the whole idea has been there before. They are used a lot in pharmaceuticals because you don't involve at all organic solvents, you just have water. But they have been having, the applications are here. Biomolecule, cell separation, drug delivery. even in wastewater treatment. And of course, in the past, they have been used mainly in batch systems. And there have been problems, though, and that's why they kind of have not taken up. One is that because the two phases are quite similar, the surface tension is, interfacial tension is very, very small. I think I have some properties later on, which means if we have a system like a mixer, where the energy dissipation, the energy, let's say the way the energy dissipation distributes in the mixer is very non-homogeneous, non-uniform, and we have areas with very high energy dissipation, very close to the impeller, and very low further away. It's microemulsions were generated. If we create microemulsions, then it's very difficult afterwards to separate the phases. So in traditional mixer settlers, we would mix the phases, try to make the extraction, and then try to keep the phases apart. If you create microemulsions, this would be very difficult to happen. And then exactly, because they have the drops are generally small, the settling times were very long. And of course, this pushes the application, makes the processes less favorable. And again, we think by using these small channels, we can avoid these problems of intense mixing and having microemulsions and this separation at the end, and I'll show you how. So just as an example, this is from something we have done, but this is usually what happens. We have the salt. This is the salt we used, potassium phosphate, and this is the ionic liquid you used. This is an imidazolium-based ionic liquid. So the amounts we add are quite small in the water. And what we see is that when we are below a certain fraction concentration, we just have one phase. And when this concentration increases, we get these two phases. Some other results is that here we have we have a top and the bottom phase. One has more ionic liquid, and we call it ionic liquid rich phase, and the other has more salt. But they are two phases. We see an interface. So this is some properties, the densities. So there is some density difference actually between the two phases, which is nice if we want to do separation of the two phases in the end based on gravity. And some interfacial tension, just to show you that indeed the interfacial tensions are very, very low. So one thing I wanted to say is that the results I'm going to show you are three different concentrations of the salt and the ionic liquid. In what we did, you can do a lot of things, of course. Just the whole phase diagram can take some work to be done. We just, because we were more interested in the separations, we decided to use just three concentrations, the same for the salt and the ionic liquid. So when we say 18%, we mean that in the initial mixture, we have 18% salt, 18% ionic liquid, 20, 25. So this is one line, this is one, and this is one. So as you increase the concentrations of these two things, we move away from this line that separates the single phase from the two-phase system. Okay, so they didn't want to spend a lot on flow patterns, but just indeed to show you that this is flow patterns we get with the aqueous biphasic systems. So it is possible, although the phases are so similar, it is possible to have two phases with quite a nice clear interface. And again, we have a flow pattern map. And what we see, we have the mixture velocity and the volume fraction of the ionic liquid rich phase, not ionic liquid phase, the ionic liquid rich phase. And again, you can start playing. We tried different sizes of the tubes. And of course, as we are in the smallest size, this is all the region of the plug flow that we were mainly wanting to work. And as we increase the size, the plug flow region decreases. So this is the map that guided us to say that if we want to have plug flow in these channels, which could be perhaps like between these two, then we need to be in that sort of area. So you do the flow pattern map in advance, you know which volume fractions of the two phases you want to have plug flow, and then you continue. That's how we did it. Yeah.
In this area, I'm not getting all the places plug flow, right?
So in this map, No. So this is the, so we have here the map is, I think is for the smaller channel, the 0.2.
One red one, right?
Yeah, I believe so. Yeah, maybe the lines, maybe they have moved. Yeah. Yeah, 0.5.
0.8.
That's right. Yeah.
So why the circle part? Means I'm not getting that circle part.
The circle. Yeah, this is the 0.8. So actually in 0.8, we only have plug flow inside here. And the rest can be, I don't remember now the patterns, could be either a drop or maybe a something like in these extremes. So this is the region where you would have plug flow. So in 0.8 is quite limited. That's what the map shows. Yeah. So and yeah, so in 0.5 is good. In 0.8 it is limited to that mixture velocity. Okay, this is logarithmic scale as well, but that mixture velocities and these volume fractions of one of the phases. Yeah.
Beyond that, it won't. There's no phase separation.
No, we are always in the case where we see, we are always in this case here. Yeah, that's that. So the concentrations of the ionic liquid and the salt are fixed. So what I have here is the volume fraction of one of the phases. Here is the volume fraction of the ionic liquid rich phase of the top phase. Okay, it's not the ionic liquid fraction; it's the ionic, it's the fraction of this phase. Yeah, yeah. So we treat then once we are above, we just treat it as a two-phase system. Yeah. If you are here, you would just have one phase. Yeah. I think we just do it with a magnetic stirrer. Yeah. So this is like a simpler. Basically, you have your little flask. You put in, mix, put in, and at some point have to do it gradually. So this work can take a bit of time because you have to do it gradually. And then at the concentration where you start seeing an interface, you know, yeah, that's where I am.
Do you decide what should be the composition of IL rich phase and salt rich phase?
No, when you have a system like that, the intention is to get this line.
No, the line will come.
Yeah.
But it does not tell where your actual system lies. When one phase can be this much, another can be this much.
So these are, no, what I'm saying is that, yeah, no, I see what you mean. This is the initial concentrations in the mixture, yeah? Because that's, if you want then to go further and to see how much ionic liquid you have here, how much salt you have here, you have to do other concentration measurements. So this is the initial concentration.
Concentration is not an issue. What I'm asking is the amount of individual phase. That means one phase, means when you are making the next, in the next slide, they are left. Let's say both should be 50-50%. How did you ensure that both should be 50-50 or 40-60? No,
that's what I'm saying. This is two different things. So initially in here, put 18% by weight ionic liquid, 18% by weight salt. 18% means that when we put them, I'll see two phases. Okay, end of story. I then have two phases, and I can take 1 ml of this and 1 ml of this, 50%, and I will run my two phase.
Okay.
Yeah.
Them separately.
Yeah. Then we treat them as separate phases. And that's what I'm saying. Once we get here, we treat them as separate phases.
Right.
Yeah. Okay. So you can do fancy things which we have not done yet, but it might be interesting to actually make this separation to happen within the channel, but we have not done that. There are, I mean, maybe we can discuss that later, but there are fancy ideas that somebody can try, which is to start with 15% of the salt and the ionic liquid, and then add a little bit more, and then induce the separation. Yeah, this might be actually very nice because if people start thinking about mass transfer resistances, you have the least mass transfer resistances when you are all in one phase. So you can think a bit creatively and say, if I actually do it like that, my mass transfer will happen and I put also my metal or whatever very quickly, and then make the two phases separate, which, yeah, but it will be more tricky to handle, to control as a system, but there is a possibility there. Yeah. So what I wanted then to show you is that there is extractions in small channels have been tried, and there is quite a bit of literature now out there. There is also a lot of literature on what extractants we need to use. I will, what we have been doing, that's why I concentrate a bit on the things we have done, because I can show you more graphs. Usually in extraction, in solvent extraction, we have an aqueous phase that contains the material we want to separate, or a mixture of materials actually, and the organic phase that will have the extractant, which is a molecule that in a way grabs the material and keeps it in the organic phase. And this is the basic, let's say, principle. Extractions have been used a lot for metal separations. Also, as we said, pharmaceuticals, there is a lot of applications. We applied it a lot on metal separations, and we tried a bit on amino acids to use it on biomolecules as well. When we have metal separations, then the aqueous phase is usually an acidic or a strongly acidic solution. And as I was saying, there is a lot of work in the literature on the things to use. How acid should be the aqueous phase, what sort of extractants or ligands you should have in the organic phase to actually enable the separation. So in chemistry-wise, there is a lot of work out there. And the other thing is that also it's something worth having in mind, especially if you try to design a process, is that in the lab now, we have one metal and we try to see how fast it happens, the separation, how quickly, how can we, what's the residence time effect or whatever else, concentration effect. Usually in practice, you will have a mixture of metals, and that's the point. You want to separate one metal of the other. So the extractants or the ligands people use, they have to be selective to some metals. So there is a lot of background work on chemistry, and a lot of it is available in the literature. What we have found, and I'll say it from now, is that actually it's good to have it as a starting point, because we are not chemists. We are not going to go to the lab and make new molecules. But what we have found is that actually, once you get away from the little batch chemistry, let's say, investigations, people might say to you, this TPP, for example, is a good extractant. But what we realize is when we actually put it in a process, in a flow, in a continuous process, then we might find that one actual extractant might be better than another, even though the literature, the chemistry tells us something different. Chemistry will report results in equilibrium. They will mix their metals. They will do this extraction over a very long time to see what is the maximum amount of metal that can go from one phase to the other. We don't do it in equilibrium. We wanted to do it continuously because the process cannot run forever. So we are also interested in how fast the separations happen. And that's why sometimes can be that one extractant is actually in practice in a process better than another. So what we found in the lab, and I've seen a lot of people actually in the literature, is that in the end, you may suggest or you may come up with a different system than what the chemistry has suggested, because actually you look at it in the process rather than at equilibrium conditions. So we have done a lot of these extractions. We focus on metals now, I can say that in the lab, because we are trying to investigate more on critical metal separations. I think at some point it was brought up. Critical metals are everywhere in all these computers, the electronics, all the renewables, in magnets, in fuel cells, in catalysts. And there is this, let's say, intention to not just mine them, but also to recycle the metals that are already in circulation. It has been used a lot. This is how we start the work as well on spent nuclear fuel reprocessing. A lot of the processes when you get the spent fuel from the reactor, a lot of these processes to recover or to separate some of the actinides and lanthanides involve solvent extractions. So it's actually a nice, very well used process. And of course, we can intensify it by using small channels, and that's how we have been working in that area. So the standard system, that's where we do our extractions. We have, again, the two fluids fed into a test section. We talked a lot about techniques. Now we are using real, let's say, fluids. We might have acids, we might have solvents, and we don't want to change their properties to get better images. We have to stick to the properties they have. Imaging is a good way to start with, because you get an idea of the flow patterns. We want to do PIV, then things get a little bit more tricky. Use of lasers would be more limited. And also we thought ultrasound that I was mentioning to you is a nice alternative, because it doesn't interfere with the system internally. And what we do, I've not mentioned it here, but people may have come across it. For the separation of the two phases, we have done some in-house, let's say, separators based on the different wettabilities of the materials at the end. But also we have been using a lot lately the Zyput separators. I don't know if people have heard them. You know, it is commercially available. It's based on membranes. So we can discuss that if you are interested. And it's also mentioned in papers. So basically, it's a membrane is based on different wettabilities of materials, like a membrane. The two-phase mixture goes there. One phase likes the membrane and goes through, the other doesn't and stays. So then we can get one phase and usually the organic, and the other phase, the aqueous, that we can pass in UVVs. And you can have UVVs instruments, spectrometers that are continuous as well, and we measure the concentrations, and that's how we get the data. We could also, in some cases, measure the concentration with UVVs again in there. So UVVs is easy, gets a lot of metals, not all of them. Some of the metals, like these, platinum, palladium, are we mine it what we call an ICP, is again a spectrometer, but is kind of slightly different. Again, I mean, if people are interested, we can discuss that. And it's not continuous.
How are we using ABS for separation, extraction?
Mm-hmm.
How are we using?
So you would, so in the ABS, what we would do in all these cases, the aqueous feed or one of the ABS phases will have the metal, and the other phase will have the extractant. So when we put them here, the metal will go from the aqueous phase to the organic phase.
So either way, whichever side is there.
It's usually that's the order. It goes from an aqueous solution to an organic solution.
The purpose of ABS is just to have,
instead of organic, to have another benign, let's say, solvent.
So if we add, means if that is already there in one of the systems, and we add the other, all the components, and we can get a phase separation.
Mm-hmm.
It does the maximum separation at that time.
With the maximum separation, what do you mean?
Right now, what is happening? You have solute.
Mm-hmm.
Separating one of the.
Yeah.
Right.
Yeah, the metal. Yeah.
ABS.
Yeah.
Create ABS once they are.
No, the ABS, as I said already, the ABS are two phases. I'm not doing anything in here with the ABS. I'm taking the top and the bottom. One goes here. I add the yeah.
The compounds actually, like you have to each other if they come in together.
Yeah, no, they will stay two phase in here. Yeah.
But the solute will be one of that.
Yes.
Instead of adding inside, if we add together and then create the second phase,
Mm-hmm.
won't it lead to the separation there itself?
You have to create the second phase, so you need to add some salt or ionic liquid to create it. I would prefer, let's discuss that afterwards, because I think this is a niche application, let's call it like this. Let's stay with the two phases at the moment, but I'm happy to discuss that later. I think we might just be confusing the message. This can be possible, as I said, but there might be limitations in terms of how well you can control or how many inputs you have. But it's a very, very interesting, as I said, idea. Yeah, and it would be worth trying. But let's stick with just having two phases here. Otherwise, you start thinking about what's the flow pattern and yeah, okay. Right, so not much chemistry. I just wanted to show something to you. Again, these things exist in papers and I don't want to make it too complex, is that there is always, if you go down this route, even if you don't do reaction, there is some chemistry to understand. These things are very well documented and it is for uranium extraction. We use some in the lab. It's depleted uranium. It's toxic rather than radioactive. That's why we were allowed to use it. We don't have a radioactive lab. But basically what I wanted to say is that there is a bit of chemistry involved always. So in this case, by changing the amount of the acidity, let's say, of the aqueous phase, we could change the partition coefficient. So maybe I should explain that a bit more. So by having also the mechanism that this extraction happens. Okay, so these things are worth having in mind when you try to do an extraction separation like that. You really need to go back to the chemistry papers and see what's the concentration of the nitric acid, what's the concentration of the extractant as well, because they will affect what we call partition coefficient. Maybe I should make a break here and ask people. Do people know what is the partition coefficient if we have two phases? Or so if you have, let's start simpler. If we have, you know that, for example, CO2 or oxygen can exist in water, aqueous phase, and also in air. Yeah. And what do we say that happens between these two concentrations if we leave them there for a bit? They get into equilibrium. Okay. So if I have a water, if I have a system like that, okay, water air, or in this case here, let's take the europium or a metal, which is the similar approach. Let's start with the CO2. So I have water, I have air. There is a lot of CO2. Then there would be a final concentration here and a final concentration here. Will the concentration between the water and the air of the CO2 be the same? That's general knowledge. Would it be the same or not? Come on. Oxygen. Would it be the same or not? Do we have the same amount of oxygen in water and in air? No, is the answer. Okay. They are still at equilibrium, but water can only take so much oxygen and air can only take so much oxygen. The same happens in this case here with a metal. I have a metal and I have a certain concentration, and the metal can happily go to the aqueous phase and to the organic phase with the extractant. How much can go, and I can leave it there for a long time. If I leave it there for a long time and I measure the concentrations, the concentration here will be different than the concentration here. Okay, they are at equilibrium, nothing more can happen. They're never going to be the same. So that's why we don't say they are the same, but we say they are at equilibrium. Okay, what we try to do is by adding the extractant, we try to shift, to move the equilibrium, because what we really want is to have most of the europium not here, but here. If we don't add the extractant, most of the europium might just stay in the aqueous phase at equilibrium, doesn't go anywhere else, doesn't move here, even though the concentration is higher. So I put the extractant, usually some sort of complexes like that form. It's physical, it's not a chemical, it's not a new molecule, it's so the bond is physical, it's complex. That's why it's called a complex. But this might mean that I can have more europium here compared to here. Okay, so there is always these two concentrations, one on one phase and one on the other, that are at equilibrium. And we need to know this as a starting point. Okay, if the equilibrium is not favorable, if europium is not going to go to the organic phase, then there is no point to try to do the extraction. Europium is not going to go to the organic phase. How am I going to do the separation? So we need to do these equilibrium studies to get this equilibrium constant, which gives me the ratio of concentrations of, in this case, uranium or europium in phase or the other. Okay, and this is my starting point. And this is what chemistry papers will give you, because they will have done that. So you can get this sort of information. If I increase the acidity, the nitric acid concentration, my equilibrium is the partition coefficient, as we call it, will get higher. And actually, I want to work in concentrations where this partition coefficient is high, because this means that I can have more of the uranium in the organic phase than in the aqueous phase, which is what I want. I want to move the uranium from the aqueous to the organic phase. And actually, in the experiments we've done, we worked with the nitric acid concentration about this range here. We didn't go higher because then it gets very acidic, and then you have to be careful how you do the experiments. Is that clear as a concept? That yes, because I want to say one more thing, and I need to make sure you understand that. Yeah? Is that clear? Okay. CO2 in water and air is never in the same concentration. And that's what you do when you have, for example, a CO2 removal. You have a CO2 in a gas, and you have the amine solutions. And you might put stuff inside the amine solutions to move to the equilibrium so that more CO2 leaves the gas to go to the amine solution. So this is what will happen. We get these experiments to get each of these points. We might have to wait 2, 3, 5 hours, because we have to make absolutely sure the system is at equilibrium, that this is all it can get between the phases. What I want to bring in, though, is the something that we are interested in as chemical engineers, which is the rate this happens. Once I bring together the, let's say, the two phases, so to get the equilibrium, what we do is that we have a small vessel, we put the mixer, we put the organic, we put the aqueous phase, we put the extractant, we mix. After an hour, 2 hours, 3 hours, we read then the concentration here and here. Okay. So this transport it doesn't happen instantaneously. It takes a bit of time. So when now we put our fluids inside the channel, we work at a much shorter time. So at the end of the channel, and again, if you've done some chemical engineering, you have gone through this concept. At the end of the channel, we are not going to have reached equilibrium. Okay, mass transfer would have happened, but equilibrium would not have been reached, because my channel cannot be that long to go for 3 hours. Yeah, that's how high the velocity is. I need a huge, very long channel to reach equilibrium. Okay, so I'm not going to be at equilibrium here. And in a way, that's all right, because that's how we work. And then we might have to have another stage and another stage. However, if this partition coefficient is quite high, yeah, then it means that a lot of the material would have transported. Not all, not at equilibrium. I actually don't want to be at equilibrium, because the closer I am at equilibrium, the slower the separation happens. Yeah, it's your concentration difference that drives the mass transfer between the two phases. Is not as, so you start going fast and then you slow down. So you really need to, and this is this can be taken care of in a process modeling, in a flow sheet modeling. Is this second concept clear as well? Okay, so we are not going to reach equilibrium. And actually, if we want to do experiments in the lab, we avoid equilibrium, because then it's very difficult to see the effects of properties, if you see what I mean. If I want to see what's the effect of concentration, everything reaches equilibrium, I'm not going to see it. So I really need to be something a little bit beyond equilibrium, before equilibrium, so I can see if I change my flow rate ratio, my concentrations, how do I affect the mass transfer? Yeah, go ahead.
Just because of it's a smaller size,
Mm-hmm.
diffusion would be significant. So won't it take much less time compared to the macro scale?
Oh, sure. Yeah. So that's the whole idea, and that's what I will discuss. So in terms of what happens in a bigger vessel, like the stir tank, things can happen much faster here. But of course, this is the mass transfer, the transport thing. You can never win over the kinetics. I mean, if something takes slow because usually they're quite fast in this case. The rate it takes to form this complex is slow.
Yeah.
You cannot beat that. This is kinetics. This is thermodynamics.
Yes,
Yeah.
but we have reduced this.
Yeah.
In the surface area.
That's right.
And
Yeah, yeah.
using the,
So you speed up your mass transfer, but yeah.
But that much time means like if it is 3 hours, then you.
That's correct. Yeah, but still, even few minutes. But we don't want. That's what I'm saying. We don't want to get to equilibrium, but definitely it does go faster. Yeah. Okay. That's for sure. I mean, because we speed up the mass transfer. The other thing that we kind of brought up here is that if the kinetics of something are slow, if your reaction is slow, you need to think whether you need a microchannel. Okay. Fermentation, I'm told, is a very, very, very slow process. I don't know if people ferment anything at home. So point to use microchannels, we have to wait, I don't know how long. You might want to use microchannels for other reasons, because your flow patterns are better or whatever, but it's not to intensify the mass transfer. So in all these cases, go to microchannels or small channels, we have to have fast kinetics, and we want to speed up the transport rates. Yeah. Okay, let me go a bit faster, but I mean, this is related to the next, so we can stop and then or go a bit more and take a bit less from the next lecture, because the two topics go one after the other. I want to introduce this, you may have come across them, these sort of parameters that we will be using. Residence time, again, we have a few chemical engineers here, is that correct? Yeah, some? One, two, okay. Right, residence time. So that's how we defined it in the channel. Will be the volume of the channel over the flow rate. So we have two different ways to define this extraction. So one is the amount extracted, and I work with the uranium because I'll show you some results. So the initial amount of uranium in the aqueous phase minus the final one over the initial one is the percentage extraction. So that's how much we went to the other phase. Extraction efficiency now, and that's why it's read out, I should have done that red, is slightly different. This is the amount extracted, the final, minus the initial, okay, how much we lost, but over the maximum could have been extracted, that is given by the equilibrium concentration, minus the initial. Basically gives us a measure of how far from the equilibrium in the end we get inside the channel. And this is also a measure because, yeah, as we will show, we can go very quickly close to equilibrium. So these are two different measures. This is the actual one. That's how much in amount I extracted 10, I don't know, 10% of 100 grams I had initially. But this tells me in the end of the channel, how far away am I from equilibrium? And then the mass transfer coefficient, there are a few definitions out there. Basically, it shows you that's how you can. So this is yeah, it's the overall mass transfer coefficient, and it includes both the mass transfer rate and the interfacial area. Yeah. So let me show you some results now. This is all for uranium because we had worked quite a bit in the beginning before moving to to other metals. Now we're working a lot more with other metals. So we have here the nitric acid concentration. As I told you, we played a bit with that, and the of the uranium. And you see here, and this is the black curve. Yep, this is the open symbols. And you can see that as we increase the nitric acid concentration, we get more extraction. In this channel, I can't remember now what's the residence time. So I had the channel that was 10 centimeters, and that's the extraction, the percentage extraction we got. So it kind of follows what we had from the equilibrium. As we increase the amount of nitric acid, this distribution coefficient increases, which means it's more favorable for the uranium to go to the other phase. What we get also is the extraction efficiency here, which tells us how far from equilibrium we are. As you can see, we are not 100%, so we at the end of the channel, we do not reach equilibrium. But in all cases, it's quite high. And then it kind of follows a little bit these curves. Let me just show you some results a bit more quickly here. What I want to bring here is this effect, just to link a bit with hydrodynamics we did before. Similar results of extraction, percentage extraction over residence time. And again, I have the, what we have here is different ionic liquids. And this is the less viscous, and this is the more viscous. And as you can see, and this is the final, let's say, percentage extractions at equilibrium. We just try to follow a little bit how quickly it takes for in one particular ionic liquid, how long does it take to reach the equilibrium? And what we found is that this increase is slower, okay, when we have the more viscous ionic liquid. And we tried to link that with the circulation times we had measured inside the plugs. And for the more viscous ionic liquid, the circulation time was quite high. So this is just to link a little bit why it may matter to also get some more details on the flow. And yeah,
its extraction is more.
Yeah.
Why should it be more?
Because this ionic liquid might be better with this extractant inside in getting the extraction out, the metal out.
This is but more viscous, right?
It's still more viscous, yeah. So that's where you really, your final decision, which one is best, is not just one criterion, yeah. And again, going back to the same idea, just because, and this is something, because I had a discussion with someone, we got some circulation times in these systems, but not with doing PIV. We're discussing how expensive it is. We did that with backlight. There is always a limit on that. If you want to use backlight, your channel not be very big, because then you have lots of shadows and reflections. So there is a kind of limit. I think that was in a 0.5 millimeter channel. We pushed it up to 1 or 2 millimeters, but really the results are not excellent. But you get some results. And we got the circulation time. And this is a nice graph that the student had done, actually, where we had the mass transfer coefficient, the blue, against the circulation time. And what we got is, forget the details, but basically we saw that the higher mass transfer coefficients corresponded to fastest circulations, the lowest circulation time. Again, shows that indeed this mixing inside the plugs does affect a little bit what happens with the mass transfer. Yeah, mass transfer coefficients, this is where you want to get in the end. So we have a mass transfer coefficient for 3 different channels. And we'll revisit this graph in the next lecture, in the follow-up lecture. And you get the best mass transfer coefficients, the highest ones are with the smallest channel. When we increase the channel size, we lose some of the intensification. The mass transfer coefficients get lower, but they are still good enough. And I have a table to compare all these mass transfer coefficients, but they're quite significantly higher than what you get in state vessels, for example. What I wanted to show you now is something that we try to dig a little bit more into this mass transfer coefficient. So we combined these experiments with some modeling. You are going to look at some CFD modeling. Some of you are doing some CFD modeling. You can do a lot of modeling in these systems. What we have decided to do, just because the modeling was not our main intention, interest, was to use this, what we call the unit cell. We called it in the previous lecture, where you have one plug, one Taylor plug, and corresponding the surrounding continuous phase. You put periodic conditions, and you can model that a lot faster. So by doing this sort of modeling, you can get results like this. Okay, so that shows us that this is the direction of flow. So this is the beginning, later in the channel, later, further downstream, and this is what happens outside. So the material does move from the plug to the surrounding phase. So if we do this sort of modeling, of course, we ignore entirely what happens when we bring the 2 fluids together. Okay, this just assumes that all the mass transfer happens mainly in the channel. will that is an issue or not. And here is I'll use those to do some comparisons. Some other mass transfer coefficients with again, at different channel sizes. In reality, what we have is that the mass transfer coefficient, stop here as you have mentioned it. The way we do the residence times in the channels is that we use channels of different lengths. Okay, because if we want to go, if we use a fixed channel length and we change the velocity to change the time, we will also change the flow pattern. And if we want, and this can be done for sure, but if we want to try to decouple, let's say, effects, what we do is that we keep the same flow rates, the same velocities, and we just change the channel length. So the residence times I report here are by actually having tubings of different lengths. And in all these experiments, we actually didn't use microfabricated channels, we just used tubing. You can get tubing, I think we said, from 0.2 millimeters up to a few millimeters, and so much more easy to use and to throw if necessary. So that's how we got the different residence times. So when we have a residence time of 7 seconds, whatever that is here, it means that our tube was really very short, and we were measuring basically just here, very close to the mixing zone. Okay. So if we want to get a longer residence time, then we cut the tube that is a bit longer, and so on and so on. So what that shows us is that in here, in the beginning, where the mixing zone is, we actually have the highest mass transfer coefficients. Does make sense, because we join the two fluids, there is a lot of mixing, new interfaces form, there is a very high concentration difference, mass transfer gets high. Once we reach the region where the plug flow is more established, the mass transfer coefficients more or less level out. They become more or less constant. So we try to look a little bit at this effect of the mixing zone using the modeling. And the other thing is we try to look a little bit more at the effect of the interfacial area. Here, this way of reporting the mass transfer coefficient, which is quite common, I mean, you find it everywhere, includes both the mass transfer, but also the interfacial area. So it was a little bit of a question. So how much of the advantage we get because we have actually reduced the specific interfacial area, the area per volume, and how much of the advantage we get because we actually have a better mixing, faster mass transfer. So to do that, we had all the measurements of the, you can do it for modeling, of course, you know the area. And that's why it's useful sometimes to measure the interfacial area. You did that with your image processing. You can get the size of the plug. You can calculate the area. And we ended up with a graph like this. And I will explain to you. It just it has a lot of information, but it's kind of easy to see what it shows. So this is now the mass transfer coefficient without the area, just due to the mixing that happens. And we have the, because we also used our modeling, we had the mass transfer coefficient, we got very close to the inlet. The mass transfer coefficient we got at the end. And the one we get from the experiment, which combines both these effects, and luckily enough, I mean, it was good, it was actually in between these two extremes. Yeah, because this one we measure contains that and some length. Okay, and we see that repeated. So what we have done here is that we have one base case. We used one situation, we had a lot more of the extractant. I'll go to that in a minute. We had a different flow and different flow rate ratios, actually. A lot of the experiments we've done are with 50-50 dispersed and continuous phase. Here we played a bit with the ratios. We are always in the same situation. Where we see some difference, if you look at the final ones, is actually this case where we used high mixture velocity. And as I said, all the numbers are somewhere, but I just want you to focus on the message. When we had higher mixture velocity, this is where the actual improvement in mass transfer became more obvious. Here, the improvements were mainly because the area is changing, but having high mass transfer, what we see is that here we are above these other base cases. And high mass transfer, high mixture velocity means we have more internal circulation and we improve the mixing. So we actually see some effect on that on the mass transfer coefficient. So plug flow is nice. We can do a lot of modeling. You can do it also in a more, let's say, advanced way by modeling the fluids from the inlets. We found that it's also okay for some results to use this, let's say, approach of unit cell. The results are much, much faster, but you lose, of course, all the effect of the inlet. I'll show you one thing with the ionic liquids and with the aqueous biphasic systems. Aqueous biphasic systems are very good. They might have a lot of problems, but they are very good for mass transfer. Maybe because there's such a low interfacial tension, it's very similar phases. So what we saw there is you look at the numbers, we get the extraction and the extraction efficiency are going to very high numbers. And actually, they're more or less the same at quite short residence times. This is seconds. So indeed, it's a good system to work with. But okay, there might be issues about controlling the phases because these are very high numbers. And this is actually from a work we did with an amino acid. And we are now trying to apply those to metals as well. Again, if people want to have references or if somebody asks you why is it better to work in microchannels, there has been a lot of literature. We have some references here from all over. And this is how the microchannels compare down here. This is for one case. This is the mass transfer coefficients. There is also this literature on jets, impinging jets. We'll talk a bit more about that in the next lecture. That also achieve, again, it is a micro system, and they do achieve very high mass transfer coefficients. And for reference, this is what you get in bigger conductors. For example, mixer settlers, you know, this is 10 to the minus 5, or rotating these conductors. There should be a bubble column somewhere else as well. Yeah, this is just to show that we do get faster, higher mass transfer coefficients. And I will close with this one because it may not be an area you are working, but in the end, if you want to use your microconductors, intensified small channel conductors for a process, you have to start thinking of the whole flow sheet because there are issues that we discussed. Okay. Let me just go to that one yeah, because there might be issues that, as we discussed, how far do we stop before equilibrium? Is it better to use one channel size or another? What concentrations? So these things require some optimization. So this is an example we were just looking where we looked at the flow sheet for separating the uranium, I think, in this case. So it's the Urex or the Purex. It's a Purex separation. So what we did is that we took the flow sheet, we found it in the literature, and we tried to see what happens if instead of the conventional mixer settlers that it was having, we were using our own microchannels. And what we needed in this flow sheet, in the end, is multi-scale modeling in a way. What we used was the mass transfer coefficients. So all this detail we had done in the lab to find the mass transfer coefficients, in the end, boiled down to, let's use this mass transfer coefficients to do this modeling. Okay, maybe some information in interfacial areas, etc. So doing that, okay, you can do it with Aspen. There are other tools as well. My colleague had their own tool, but in the end, you have a flow sheet. You have to do certain separations, and you have to make some decisions. And the decisions might be how much of the extractant to put, where do you stop, how long, what residence time you should allow, and so on. And this information, that's why it's worth having this in mind. This information of what you do in the lab to get some of these values in the end will boil down to some numbers that will be going into flow sheets like this. And this was actually a very interesting exercise because it came back to us with some sort of findings. We did manage, for example, to reduce a lot the solvent usage here. We didn't do it with ionic liquids, we did it with conventional solvents. We managed to reduce a lot the amount of the solvent, the footprint, all the residence times were much shorter, and there were some other secondary benefits. For example, because we're not using, everything was faster and the solvent was less, and we were losing less solvent in the end because, you know, by reusing the solvent, you degrade it. So it's just an interesting exercise. And of course, once you get to this level, you have to think, what do I want to optimize? What am I interested in? It might be the maximum recovery, it might be the less use of solvent, might be to be safe in that case. And actually, we are finishing here, and I'll stop on this one. And we will continue with the scale up. Actually, it's nice to have these lectures together because then we are going to be talking